Hi, I'm Jonathan, and over the semester I worked on this project of doing parallelized data transformation to validate a physics simulation of a solar-powered car. I'd like to start off by thanking my supervisor, Lee Shepard, and also Rosalind Wang for their help throughout the semester. Some of the goals of the project were to develop a convenient telemetry data transformation pipeline so that telemetry data is easier to handle in the future. Secondly, it was to determine the accuracy of the simulation that we'd built and also determine where future work is required to make this simulation better. And then finally, to look for ways to improve on data collection practices for future races. To provide a bit of context, the Bridgestone World Solar Challenge is a biennial 3,022-kilometer event from Darwin down to Adelaide, and the goal of the event is to be the first across the line. And the event has strict regulations on how you can build your car. And the result of this is you have quite a limited energy budget to complete the race. So you have to manage your speed. That leaves us with a race strategy of go as fast as possible while still finishing the race, which gives us the need to simulate our power consumption ahead of time. Here's an overview of the data that we were transforming. So it came in the format on the left, which was a raw list of telemetry packets received from the car. And we wanted to transform it into this format on the right, where we have all of the variables that happened within a given time frame, rather than just a list of things that happened. A MapReduce technique was employed because it is theoretically faster for this sort of task. So we mapped into key value pairs, with the key being the timestamp and the value being the labeled column name. We used the reducer to get all of the things that happened within that second, and finally it would put that in the output data frame as a single row. Apache Spark was chosen for this, and it's an open source processing and analytics engine. It can be used to distribute a computing job over different workers to get it done quicker. The size of the data we were working with in this case wasn't quite large enough to see a lot of those speed benefits, but it was still marginally faster. AWS Glue was chosen, and it's a managed and serverless way to run Spark, which basically just means it's easier to use. A quick overview of the simulation. We're mainly focusing on the three forces that are resisting the car going forward, which are aerodynamic drag, rolling resistance, and gravitational losses. And then the motor of the car has to overcome those. So the general validation approach was take some variables from the real-world data to set up the same scenario, and then compare the simulated power consumption to the actual power consumption. So in this case, we're taking real-world speed and real-world location of the car and comparing the output. So here are the final validation results using data from the 2017 Bridgestone World Solar Challenge, where the orange line is simulated power consumption. We can see that it generally follows the real data quite closely, but is generally underestimating, as it's generally lower than the blue line. Here are some metrics for that comparison. The mean absolute error being 460 means we're on average off by 460 watts. And then the total amount of energy accounted for by the model over the course of the race was 75.6%. So we can see that we're generally underestimating power consumption by roughly 460 watts. Here's plots comparing simulated and actual power and speed values. And we can see that generally the shape is followed between both of them. However, the simulation isn't accounting for the periods of very high power consumption, as the simulated data caps off at about 2 kilowatts, whereas actual data keeps going all the way up to 3. So some future work to be done is to decode the weather station data from the weather station on the chase vehicle, which will basically just give us more granular data. Decode the solar panel data off the car to better validate power in. Investigate dynamically simulating motor efficiency. Investigate modeling acceleration differently, and determining which conditions lead to the simulation being inaccurate. And then determine if there are future controlled experiments we can do with the car to better understand its performance characteristics. And thank you very much for listening.